So getting back to our discussion of climate change and combustion of fossil fuels, we can write a balanced chemical equation that represents fossil fuel combustion. Now, fossil fuels are a mixture of lots and lots and lots of different compounds. So we have to do some approximating here. So we're going to use octane as a representative fossil fuel. So this is octane, and yes, that is the thing that they talk about on the gas pump, octane rating. This is the octane. It's 8 carbons and hydrogens to make 4 bonds for all the carbons. So 2 octane molecules will react with 25 oxygen molecules, and they'll form 16 carbon dioxide molecules and 18 water molecules. So those numbers seem like bigger than what we usually see in chemical reactions, but that doesn't mean they're wrong. So we have information here. We see that we're going to get 16 CO2 molecules for every 2 octane molecules that burn. Or, instead of looking at individual molecules, we could look at dozens of molecules, or chemist's dozen, the mole. So we can say, well, 16 moles of CO2, and you can think of that as inserting the unit mole here, are produced for every 2 moles of octane. And that's usually how we interpret chemical equations, because we're almost never just doing individual atoms and molecules. So the coefficients give us the relative amounts in moles of each substance. So the amount of every substance that's used and every substance that's made in a chemical reaction is related to the amounts of all the other substances. So we have to obey the law of conservation of mass, because just like the law of gravity, you can't just say you're not going to do it today. So we balance the equations by balancing the atoms, which we just saw how to do. Now, the study of these numerical relationships between chemical quantities is called stoichiometry. So you've probably heard that word before, stoichiometry. I'm not going to quiz you on it or ask you to spell it, but if I say stoichiometry, you should have kind of a clue of what we're talking about. Okay, so I hope everybody had dinner. Let's talk about making pizza. Because this can help us to see the relationship between ingredients without that cloud that comes over our eyes when we talk about chemicals, right? So if we look at this as a very simple recipe for a pizza, 1 crust, 5 ounces of tomato sauce, 2 cups of cheese, put that together and bake it and you get 1 pizza. Okay, it's a recipe. A chemical equation is much like a recipe. It tells you what ingredients you need to put together, and then it tells you what you're going to get. Like if you make this cookie recipe, you're going to get 3 dozen cookies. Except you never do, because you end up eating half the dough. But that doesn't happen in chemical equations. So we can look at this recipe mathematically and say there's 1 crust to 5 ounces of tomato sauce to 2 cups of cheese to 1 pizza. It's ratios. And we can calculate how many pizzas we could make from 10 cups of cheese. Now, most of you can probably look at that and say, well, 5, but how do you do that? You did that in your head. This is what you're doing, not even thinking about it. So 10 cups of cheese, and we're trying to figure out how many pizzas. This is dimensional analysis. We have cups of cheese, we want to figure out how many pizzas. So we want to divide by cups of cheese, so those units cancel out. The relationship is up here in this recipe, this equation. there are 2 cups of cheese needed for every 1 pizza. 2 cups of cheese for every 1 pizza. We get 10 divided by 2. We can make 5 pizzas. Any questions? Same thing works with chemical equations. Instead of dealing with cups of cheese or ounces of sauce, we're going to be dealing with moles of molecules, which is like dozens of eggs, right? It's really not that unfriendly. And we can relate any 2 factors here. We can say 2 moles of this for every 25 moles of oxygen. For every 18 moles of water that's produced, 16 moles of carbon dioxide will be produced. Okay? So if we burn 22 moles of octane, how many moles of carbon dioxide form? This is just like the cheese to pizzas. 22 moles of C8, H18, and I want to know how many moles of CO2. So I'm going to divide by the previous unit. That's an 8. I'm just converting units. The ratio of moles of one thing to moles of another is the it's the coefficients in the balanced chemical equation. So 2 moles of octane, give us how many moles of CO2? 16, right? It's just literally that number is going in here and this number is going in there. Now, could you simplify that to 8 to 1? Of course you could, but why? You're going to use your calculator anyway, and sometimes you have a brain fart when you do that and you end up with 7, which is wrong, and then you get the whole thing wrong, which is dumb, so just use a calculator. So I've got 22 times 16 divided by 2. 176. These coefficients are exact numbers because when it comes down to it, it's exactly 2 molecules of this produce exactly 16 molecules of that. So the coefficients do not affect the sig figs. I started with 3, I'm going to end with 3 moles of CO2. 176. We're getting a lot more moles of carbon dioxide because each mole of carbon dioxide only has 1 mole of carbon. And each mole of octane had 8 moles of carbon. Right? Any questions? Of course, we don't measure things in moles. We measure things typically in grams. So we have to do some dimensional analysis when we do stoichiometry problems. And this is probably the biggest place, the most important place, where understanding dimensional analysis will make doing these problems much simpler. So this is the general path. Mass of one thing, you're going to convert that to the amount of it in moles. You go from mass to moles using the molar mass. Then moles of A to moles of B, coefficients in the balanced equation. Moles of B to mass of B, its molar mass. So I like to abbreviate this even more. Grams to moles to moles to grams. And you should get to the point where you wake up mumbling that in your sleep. Grams to moles to moles to grams. Oh, nightmare. Right? Grams to moles to moles to grams. This is the starting point for any stoichiometry problem. We'll get into things with liquids and gases and other stuff happening, and it's all just a variation of this. Grams to moles to moles to grams. Okay, according to the U.S. Department of Energy, the world burned 3.3 times 10 to the 10 barrels of petroleum in 2013, the equivalent of approximately 3.7 times 10 to the 15th grams of gasoline. Calculate the mass of CO2 emitted in the atmosphere using the combustion of octane as the representative equation. So let's see what they're giving us. They're giving us this many barrels of petroleum and this many grams of gasoline. And what do they want us to find? Mass of CO2. So CO2 is the thing we're trying to find out something about. And now this is talking about petroleum and gasoline, and neither of those are in here. This is not typically how the questions end up being, but it says use the combustion of octane. So this is what we're referring to for this mass. So you always need a balanced chemical equation, and then I like to use it to organize the information. So we have a mass of gasoline, which we're going to approximate as octane. So this is 3.7 times 10 to the 15. 10 to the 15th grams of that. And what I want to know is over here, it says mass, didn't give me a unit. What unit would be convenient? This was grams. It's easiest to just keep with the same unit. So we're going to look for grams of CO2. Okay? It would be possible to go from grams of octane to grams of CO2, but you'd have to go calculate a special conversion factor, which would in fact involve the very same steps that we're just going to write into the middle of an equation, and we're just going to do it all at once. So the path is grams of C8H18 to moles of C8H18 to moles of CO2 to grams of CO2. Grams to moles to moles to grams. So that tells me what's in the top of all my fractions. I have 3 arrows. I'm going to have 3 conversion factors. This is the starting mass. And so now it's just like converting centimeters to miles or something. I highly recommend writing the chemical formula because we have grams of octane and we have grams of CO2. We have moles of each. We don't want to get those mixed up. So that many grams of octane times and a line. Times and a line. Times and a line. So here's Dora. Grams of octane to moles of octane. And after that, we'll go to moles of CO2. And then we'll arrive at grams of CO2. Cheering and confetti. Grams to moles to moles to grams. Grams to moles to moles to grams. I need this unit to go away, so I'm going to divide by that. So I'm going to divide by C, grams of C8H18, so that those guys cancel out. And I'm going to divide by moles of C8H18, so those cancel out. And I'm going to divide by moles of CO2, and those cancel out. Now we have 3 conversion factors that we need numbers for. I like to do the middle one first, the moles in the middle, because it doesn't involve any calculations. The mole ratio here comes from the coefficients in the balanced chemical equations. That's it. So for C8H18, it's 2 moles of that and 16 moles of CO2. Again, you don't need to simplify that. Just write the numbers down as they are. The calculator will take care of it. Now we do have to do some calculating. So grams to moles, moles to grams, we're going to use the molar mass. So we've got the chemical formula. So we'll just write some little notes to ourselves down here. I need 8 carbons times their mass plus 18 hydrogens times their mass. And this is going to give me 114.224. If we think about sig figs, and we should always think about sig figs, it's usually our starting number that's going to limit things. This has 2 sig figs, right? So as long as this has more, it really doesn't matter. We might as well just write down all of them, because, I mean, there's only 6 digits. 114.224 grams is 1 mole of octane. And then we need the molar mass of carbon dioxide. So we've got carbon plus 2 oxygens is 44.01 grams. So I'm finding the mass of 1 mole. It's always the mass of 1 mole, not how many moles in 1 gram. So I don't have to think about, am I supposed to multiply by the mass or divide by the mass? Because the units are there and they tell me where to put the numbers. And then I just go left to right. Now this one does have scientific notation in it. So 3.7 EE15. And I'm going to divide by 114.224. Multiply by 16, divide by 2, multiply by 44.01 equals so this should have two significant figures, 1.1 times 10 to the 16th grams of CO2. Any questions? This is like one of the staple calculations in chemistry. Stoichiometry problem going from grams of one thing to grams of the other thing. It's really important to understand how this one works, because then when we need to change up the ends a little bit, it won't be a big deal, right? So if you need some help with this, please ask me. Okay, really important. Okay, let's compare the result here. So petroleum combustion produced 1.1 times 10 to the 16th grams of carbon dioxide per year, our estimate. And volcanoes produce about 2 times 10 to the 14 grams of CO2 per year. It's a little hard to compare those numbers. I mean, obviously this one's bigger. Let's find out how many times bigger it is. Let's take the big one and divide it by the smaller one. 1.1 times 10 to the 16th grams divided by 2 times 10 to the 14 grams. $55. Now this is an estimate, right? Because I mean the volcano thing here is an estimate. It's only 1 sig fig. And so, technically this has 1 significant figure, so it would be rounded to 60. Petroleum combustion produces 55 times more CO2 than volcanoes. So if CO2 is the problem, I don't think we need to worry about capping the volcanoes or doing something with that, right? It's us. Any questions? Let's do another one. Magnesium hydroxide, the active ingredient in milk of magnesia, neutralizes stomach acid, primarily HCl, according to the reaction. Now that's kind of like backstory. We don't actually have to know any of that. Here we've got our balanced chemical equation, and then we got the question. What mass of HCl in grams is neutralized by a dose of milk of magnesia containing 3.26 grams of MgOH2? So they're giving me a mass of MgOH2, and they're asking me for HCl in grams. Now, it's not saying how much HCl is produced, but it's saying how much HCl will this amount react with? How much will it neutralize if you take this much milk of magnesia? So we're given a mass, so I'm going to write that mass up here, 3.26 grams of that, and question mark grams of this. I'm given grams of one thing, I'm asked for grams of the other thing. This is grams to moles to moles to grams. Grams of the thing I have a mass for, to moles of that thing, to moles of the other thing, to grams of the other thing. Grams to moles to moles to mole, grams to moles to moles to grams. The moles are in the middle. I sometimes see people with moles to grams to moles, and that just really does not work at all. Malcolm in the middle, moles in the middle. They're always in the middle. So 3.26 grams of MgOH2. And the next unit is moles of MgOH2. And I've got another arrow, and that's going to give me moles of HCl. And another arrow, and I get to grams of HCl. Grams to moles to moles to grams. In this first step, the compound is staying the same and the unit is changing. In the middle, the unit is the same, the compound is changing. And at the end, the unit is changing and the compound is staying the same because you can only change one thing at a time. So put in the units so they cancel out. Okay. Let's do moles in the middle first. What number am I going to write in front of moles of HCl? What number is in front of HCl up here? Okay. So HCl is a 2, and what goes in front of MgOH2? 1. There's not anything written here, right? But if we had to put a number there, it'd be 1, right? So, you don't have to put a number down here, but a lot of people don't feel comfortable without a number there, so that would be 1. And then we have to go calculate some molar masses again. Magnesium, 24.31. So 24.31. How many oxygens in this compound? 2. 2 times 16. And how many hydrogens? 2. Calculator went to sleep. 58.326. My starting number has 3 significant figures. The mole ratio is exact. This is more. We could say, well, it's only 4 sig figs. It's just not even really worth thinking about. We don't want to use rounded numbers anyway, so let's just write them all in there. And then HCl 1.008 plus 35.45, so 36.458 grams. .26 divided by 58.326 times 2 times 36.458. 4.0754 grams, 4.08 grams of HCl. Any questions? One more example. A component of acid rain is nitric acid, which forms when NO2, a pollutant, reacts with oxygen and water according to this simplified equation. 4NO2 plus O2 plus 2H2O gives 4HNO3. And as you can imagine, having nitric acid in your rain is not good for much of anything. It's really bad on marble statues and concrete and trees, and it makes the rivers acidic. It's just not good. The generation of the electricity used by a medium-sized home produces about 16 kilograms of NO2 per year. Assuming that there's adequate oxygen and water, what mass of KNO3 in kilograms can form from this amount of NO2 pollutant? Well, what number are they giving us? 16 kilograms of NO2. And they want to know kilograms of HNO3. So this is what we're going to find, and this is what we're going to start with. Oh, that's the wrong yellow. That's what we're going to start with. So it's saying 16 kilograms, and we want to know the number of kilograms of nitric acid. Well, what did I tell you the path was? Grams to moles to moles to grams. Can we do that exactly here? No, because it's kilograms. So grams to moles to grams. But first it's kilograms to grams. And then at the end, it's grams back to kilograms. What we'll see is that those conversions at the beginning and the end cancel each other out, but let's pretend we don't know that for now. So 16 kilograms of NO2. I'm going to convert that to moles of NO2. No, not yet. Not yet, I'm not. Grams of NO2. You got to look at the path, or you'll get lost, and the trolls under the scary bridge are going to eat you. Moles of NO2. Moles of HNO3. Grams of HNO3. kilograms of HNO3. Using the kilograms makes for a lot of extra work here. Kilograms cancel, grams cancel, moles cancel. Moles cancel. Phew. Well, let's start with moles in the middle. Here I've got moles of HNO3 and moles of NO2. What numbers go in front of these guys? 4. They're both 4. 4 NO2s give you 4 HNO3. So of course you could simplify that to 1 to 1, but I'd rather write it down. Kilograms to grams, what does kilo mean? 10 to the plus 3, right? So here I've got kilo in the denominator, so I'm going to write what it means on the other side of the line, which is 10 to the 3. So 1 times 10 to the 3 and 1. And then over here we have kilograms and grams also. Here, kilos on the top, so 10 to the 3 goes on the bottom. And, if we've got our wits about us, we can see that this number and that number are going to cancel each other out. But if we don't see that, our calculator will take care of it for us and it'll be okay. We have grams and moles for our 2 different compounds. We have to calculate molar masses again. So NO2 is 1401 plus 2 times 16. .01. And then HNO3, 1.008, 14.01, and 3 times 16. .018. So this is the number for the HNO3. Grams are on the top, so the number goes on the top, 63.018 to 1. And then over here I have moles and grams for NO2, and 46 goes with grams on the bottom. (16) times 1 EE3 divided by 46.01 times 4 divided by 4 times 63.018 divided by 1 EE3 equals did not mean to do that. This line, I touched something wrong. The answer is 21.9 kilograms. No, it isn't. It's 22. I had plans for that equation. Any questions? I want to show you a way that you cannot have to put all those conversions in there. And just just ignore those symbols at the bottom there. So we're starting with 16 kilograms. Kilograms of NO2. And I wrote the kilo in red. Because what I'm going to do is I'm going to cancel out grams, and I'm just going to leave the kilo sitting there. And then I can cancel everything else out. So I'm going to go to moles of NO2, a gram of NO2. So the grams cancel out, but the kilo doesn't. It's just a multiplier. It doesn't have to be canceled as well. HNO3, moles of NO2, grams of HNO3, moles of NO2, no, HNO3, no, I meant to do that. Now, if we look at the units, I'm ending up with grams and the kilo. So for some people, that'll make sense. Other people, not so much. And I don't want to, there's other ways to think about it, but I don't want to confuse anybody. Any questions? Sometimes slow and steady, doing all the stupid little steps takes longer, but you get the correct answer every time. That's the way to go, right? Some people are looking for shortcuts all the time, and sometimes they work, and sometimes they end up getting lost, right? So you need to find what works for you, okay, in terms of things with units like this.